Hi guys, welcome back. Happy Monday. We're going to do our last lesson of the year. It's also the last topic that is covered on the BC Calculus summer work. So this is a video that will also be posted on that Google Classroom so you can access it during the summer if you need a quick refresher on how to do implicit differentiation. Okay, so we've learned our basic rules for finding derivatives, which are your power rule, product rule, quotient rule, chain rule, trig derivatives, base E, and ln. Okay, so you should have those somewhere, a list of all your rules. Implicit differentiation is more of a technique, and we use it when we're trying to find derivatives of non-functions. So everything that we've been finding the derivative of so far has been in the form of y equals, right? Y equals some function of x, which means it is in fact a function. But what happens if you have something that looks like this? So here we have a graph, but it's definitely not y is a function of x because it fails the vertical line test. So that doesn't mean that we still can't find the derivatives, the slopes of the tangent lines. The problem is that the slope of the tangent line doesn't just depend on x. So if we look at this value right here, when x is -2, normally we've only needed the x value to find the slope of the tangent line. We'd plug 2 into the derivative and get our answer. But now looking at this graph, there's actually 3 points on this graph where the x coordinate equals -2. So if you're trying to find the slope of the tangent line, the question would be, well, which tangent line? The one here, which obviously would have a negative slope. The one here, which would have a positive slope, but not very steep. And then same thing here, positive slope, but not as steep. And we can't say it would be equal to this one either. So how would we find derivatives there? So that's what implicit differentiation gets used for. So the rules that we're going to use are going to be the same, but the technique's a little bit different. And this graph is one that we're actually going to come back to, and we're actually going to find the equation of the tangent line at this point. All right. Okay, so we're going to use this one as our first example and go through the steps. There are 4 basic steps when you're doing implicit differentiation. So the question is, how would you find dy dx? So we like to use this notation because it really exemplifies the fact that y is the dependent variable, x is the independent variable. So you're taking the derivative of this equation. I don't want to call it a function because it's not necessarily a function, but you want to find the derivative of this equation treating x as an independent variable and y is the dependent variable. And what that really means is that y is a function of x. Y is not just the variable, y is a function of x. So like when we did product rule and quotient rule, we used u and v as functions of x. It's the same thing here. Okay, so our first step is always going to be to differentiate both sides of the equation with respect to x, which is what we do when we're finding derivatives in the form of y equals as well. Because on the left-hand side, we always get y prime or dy dx. But now we have to treat y as a function of x. Now, if it's possible to solve this function to get y by itself, we would do that and then just take the derivative the way we always have. But because we've got y cubed and y, there's no way to get y by itself. All right, so there's no way to get y by itself in this equation before we take the derivative. Okay, so we're going to take the derivative with respect to x, treating x as the independent variable, any other variables as some function of x, of both sides. So everything's going inside the brackets. So we're going to start with our first term, which is derivative of x squared is just 2x. Now here, we have to use a chain rule because we're treating y as a function of x. Y could be 3x plus 7, y could be 7 minus x, y could be cosine of x. It's some function. So therefore, the chain rule has to be applied because we have a function to a power. So we'd multiply the 3 times the -2 to get -6. Y, keep what's inside, subtract 1 from the exponent, and then you multiply by the derivative of the inside, which we can call y prime or dy dx. I like to use the dy dx notation because if you write y prime, it looks like y to the 1, and that can get confusing when you've got y to the 2 and other functions of y in your equation. So I like to use dy dx. So this is your chain rule. So you did the power rule, kept what was inside, subtracted 1 from the exponent, then multiplied by the derivative of the inside, which we would just call dy dx. Same thing here. So here we just have 4 as a coefficient, and then we just have to take the derivative of y, which is not 1, because y is not the independent variable. The derivative of y would be dy dx. And then don't forget, over on this side, the derivative of a constant is 0. All right. So this is actually the only calculus that we need to do when we're differentiating, because technically now we've got a differential equation. but we want to get dy dx by itself. So the rest of the steps are just going to be algebraic steps. So our step 2 is going to be to get all the terms with dy dx on one side of the equation and all the other terms on the other side. It doesn't matter which side you pick. You might get an expression that looks a little different than somebody else's, but they would still be equivalent. So I think I'm going to keep the 2x where it is, add the 6y squared dy dx over, and then subtract the 4 dy dx over. So now we did that. Again, that was just algebra. Step 3 is going to be to now factor out the dy dx. Since on one side of the equations, every term should have a dy dx, we should be able to do this. So it's basically just GCF, all right? So now we've taken the dy dx out of that right side of the equation because each term had it. And now to get dy dx by itself, we just have to divide over. So our fourth step is to get dy dx by itself by dividing each side by the factor not containing dy dx. So that would be this factor here. We're going to divide it over. And this one actually does reduce. If you left it like this, it's fine. But if you notice, you could factor out 2 from the top and from the bottom and cancel it, and we'd be left with this first derivative. But notice how the derivative doesn't depend on just x. So think about the graph that we looked at originally. You can't just know the x coordinate. You need to know the x and the y coordinate in order to find the slope, right? The derivative. Okay, so now we're going to do the example from the graph that we actually saw originally. All right, this one has a really funky graph. If you want to try to graph it on Desmos, it looks kind of weird. It has like a hyperbola and a circle in the middle. So you can graph these on Desmos. You can't graph them on your graphing calculator because you can't get y by itself. But Desmos is really a good tool to use to graph these non-functions. Okay, so this is the one that we actually saw the graph of. All right, so again, it says find dy dx of y cubed plus 3xy minus 5y minus x squared equals -4. So we're going to do step 1 first, which means we're going to take the derivative with respect to x of both sides of the equation. All right. So each term we have to take the derivative, and we have to think about what rule we're going to use for each one. So y to the third, this one's going to be your chain rule because y is a function of x and we're cubing it. So we take the derivative of this cubed first. So multiply the 3 out in front, subtract 1 from the exponent. We're going to get 3y squared, and then multiply by the derivative of y, which is dy dx. For the next one, 3x times y. Remember, y is a function of x. So this we have to use product rule on because 3x is a function of x and y is a function of x, and they're being multiplied. So you have to use product rule here. So I'm going to do u dv plus v du. U is going to be 3x. dv is going to be, v is going to be the y, and then do the product rule. Here we're just going to get minus 5 dy dx for the derivative. Here, since x is the independent variable, we're just going to get minus 2x, and then we'll get equals 0. So this is what we get when we take the derivative of all 5 terms. So here we got our 3y squared times dy dx. There's our chain rule. Now our product rule, u dv, the derivative of y is dy dx, excuse me, plus v, which is y, and then du, the derivative of 3x is just 3. Now we've got our derivative of minus 5y is minus 5 dy dx. Here we just did a power rule. We get minus 2x and then equals 0. So now the rest of it is just going to be algebra. So we're going to get all the dy dx terms, this term, and this term on one side of the equation and the other 2 terms on the other side. So I actually kept the 3y squared dy dx, the 3x dy dx, and the minus 5 dy dx on the left. And I added over the 2x, subtracted the 3y. We like to put the negative term second if we can. Sometimes it's hard when you have a negative out in front with an equal sign. So if you wrote negative 3y plus 2x, that's okay. But this is just the format that we're going to get used to. So now step 3 is to factor out the dy dx from one side of the equation. So that's the GCF on this side. So when we factor it out, you can put it behind, you can put it out in front. It doesn't matter. But you've got 3y squared plus 3x minus 5 equals 2x minus 3y. And now our fourth step is just to divide that over. And at that point, nothing's going to reduce. We can't factor anything out of the top or the bottom, so therefore this would be our final derivative. But again, dy dx depends on x and y, not just x. So now let's go back to that graph that we talked about. And we saw that at x equals -2, there were 3 different points. So we've already found our derivative. It says find the equation of the tangent line at the point -2, 0. So if you go back to the original function, which I can do, if you look at this, -2, 0 should be a point on this equation. If it's not, then it's not going to work. So if I let x equal -2 and y equals 0, so if y is 0, this will be 0. This term will be 0. This term would be 0. And if x is -2, -2 squared is 4. -4 equals -4. So yes, that point is in fact on our original function. And we want to find the equation of the tangent line. So point and slope. Well, we know the point. To find the slope, we're just going to evaluate the derivative when x is -2 and y is 0. So we replace x with -2, y with 0, replace y with 0, replace x with -2. The numerator ends up being -4 minus 0, which is -4. The bottom becomes 0 minus 6 minus 5 is -11. Reduce it, and you just get +4/11. So we've got our slope and our point. We can write it in point slope form, but this one's pretty easy to get y by itself. Just distribute the 4/11 to both terms, and we get y equals 4/11x plus 8/11. And I graphed it on Desmos so you can see it. All right, there's our original curve that we looked at, and our point of tangency is at -2, 0, has a slope of +4/11, and it is tangent. If you wanted to find the tangent line here, you'd need to know the y coordinate. We know x is -2, but you'd need to know the y coordinate in order to plug it in. All right, so let's look at our last example, and the last one involves base e. Okay. So again, we're trying to differentiate, so we're going to find dy dx, which means y is the dependent variable, x is the independent variable. So our step 1 is going to be to differentiate everything with respect to x. So we're going to take the derivative with respect to x of e to the 2x minus y plus 2y cubed equals 7x. And remember, if you can rewrite your original function and get y by itself, do that. But here, since we have a y in the exponent, we have a y cubed here, it's impossible to get y by itself. So it might be possible, but it could be very, very long and time consuming. You only want to do it if it seems easy. So we have to take the derivative of e to the u. So this is one of our rules that we talked about with chain rule. The derivative of e to the u is e to the u times u prime. So we're going to get e to the 2x minus y, keep what's inside, then multiply by the derivative of the inside. So the derivative of 2x minus y would be 2 minus dy dx. All right, so there's our e to the u times u prime, making sure that it's in parentheses. All right. And then over here, we've got our chain rule again. Remember, y is a function of x, so we get 6y to the second. And then we have to multiply by the derivative of y, which is dy dx. And then the derivative of 7x is just 7. So now we've done the calculus. Now we just have to get dy dx by itself. So we have to do some distributing first. So for number 2, we're going to distribute the e to the x to both terms to get rid of these parentheses. And then we want to bring the dy dx terms over, or the 7 over. So the dy dx terms I'm bringing over to the right. So this one got added over to this side. This one gets subtracted. And then to bring over the 7, we had to subtract it over here. So again, this is just all algebra manipulating the equation. So that was step 2. We got the dy dx terms on this side. So now we're going to factor out dy dx from that side. We've got e to the 2x minus y minus 6y squared. And then the last step is just to divide over this factor and reduce anything if we can, but I don't think anything's going to reduce. This is as simplified as we can get. So 2e to the 2x minus y minus 7 all over e to the 2x minus y minus 6y squared. And remember, you can't cancel out the e to the 2x minus y's because you've got subtraction on the top and the bottom. Only if you could factor it out can you cancel. All right, so we would just leave it like that. And now we could find slopes of tangent lines. If we knew a point on the original curve, we could now plug it in there. Okay, so for your last assignment,